and go through the analysis of the electrostatic deflection of electrons. This is take 2. Hopefully you can see Excel spreadsheet right now. What I have done is I've set up a data table here. In this cell, what I did is I calculated the speed of my electrons as they left the accelerating potential and entered the deflecting field. I was using accelerating potential of 1.52 kilovolts. You will be only using 1,000, so your speed is going to be very different. Here, I calculated my times in seconds. Okay. A couple of things to note here. Okay. The $ on this A5, that is $A, $5, is so that when I copy this equation down, the cell address is locked and it doesn't advance. The same with this H, $3. The 100 in here is to convert from centimeters to meters so that my times are truly in seconds. In this column, what I have are my times in nanoseconds. You want to work in nanoseconds and millimeters. It's going to keep your graph clean and neat. Okay? And then these are the deflecting potentials that I recorded. Now remember, you had a different accelerating potential. You will also have a different deflecting potential. Okay? So your values will not be the same as mine. So now we're going to construct a graph. Most students select the data ahead of time. I don't personally do that. I like to construct my graph. I want a scatter graph marker only, and then insert my data. So I right-click on it, I say select data, I add a series, and now I can add my times. Why do I do it this way? I just hit enter to return instead of hitting that arrow. Because I don't always have my X series first. But this way I can always manually select my X series. To add chart titles and axes and things like that, you can do so here. Horizontal is in time. You're going to want to work in nanoseconds. I'm going to add a vertical title. And my vertical title is going to be the deflection. In millimeters. So this is what my graph looks like. I want to add a trend line. You can do it up here. I like to do it this way. That's just the way I learned to do it. Display equation, display R squared. Okay. This is a second order polynomial. So let's talk about what this means. Let's start with the R squared. Remember that the R squared is basically a prediction of how well the data points will fit your trend line. 0.9977 is pretty good. You can see this point right here is off. These two are off a little bit. That's probably why it's so low for this experiment. Okay. You will also need to do a regression to get the uncertainties in these values. To do that, be in a blank cell, you go to the Data tab. On the far right, it should say Data Analysis. Okay. I've done this previously today. If not, so it came up to regression. You scroll down, and it will say regression. Okay. Input your Y range. We have a problem here. I need to cancel out. The problem is, this is a quadratic equation. I need both t and t squared data to do the regression. I calculated it before I hid the column. Now we can go back to the regression. Duh, it's right here. Input the Y range, my vertical values. My X range is going to be both the time and the time squared columns. I want my output range to be up here. You can always, to return back to the screen, you can always hit enter, or you can hit that up arrow. And I'm going to say okay. Remember, this is the only part of the table. I'm going to change it to yellow so it attracts your attention. That is important. Okay. Now, remember that the standard error is the uncertainty, and it may only have 2 sig figs. So what I'm going to do is I'm going to fix sig figs right away. These coefficients should match the trend line. Now I can go back and I can change these, format trend line label, change the number, and have it show the correct sig figs. These coefficients should match what's on your graph trend, and they do. Okay. I'm going to edit my trend so that it reflects the correct variables. I didn't graph y and x, I graphed y and t. Okay. So what do these mean? The intercept, we're looking at the deflection as a function of time. We assume we had a constant electric field. Is that assumption valid? Let's look at the R squared. R squared is 1.9977 before I set it to 2 decimal places, which means that my data is quadratic. If my data is quadratic, the only way that can happen is if my acceleration is constant. Okay. So if my acceleration is constant, it means the force on the electron was constant, which means the field was constant. So yes, our electric field was constant. Okay. The general form of deflection is y is equal to y0 plus v0t plus 1/2 at squared, which means the intercept is my y0 value. Okay. Now, I'm showing you how to make this a subscript. I typed what I wanted. I'm going to go, I highlighted it on the bar. I go into font and I select a subscript. X variable 1 is the coefficient of t. What that means is that it is the initial velocity in millimeters per nanosecond. Again, I can go in and change that 0 to a subscript by going into font. Oh, okay, it worked. X variable 2 is not the acceleration. Remember, it's 1/2 at squared. So this is a over 2 in millimeters per nanosecond squared. I'm going to auto size this column so you can read this. I can change this to a squared as well. By going back into font and selecting superscript. So we have our y0, we have our v0y, and we have 1/2 a. To get the acceleration, I'm going to do it this way because I want to be a little bit lazy. This is no longer a over 2. This is just going to be a. It's simply going to be the coefficient times 2. What about the uncertainty in A? We're doing multiplication and division, which means we use relative uncertainties. Delta A over A is equal to delta coefficient over coefficient. That means delta A is equal to A times delta coefficient over the coefficient. Again, let's set these so that they're the correct precision. At this point, what you have left is to calculate the acceleration and the velocity in standard SI units, meters per second squared. Be careful with the acceleration because of that time squared. Okay. Your accelerations should end up being on the order of 10 to the 14th, 10 to the 15th meters per second squared. Okay. Calculate the force on the electron, calculate the electric field. Okay. Now, before we go, I want to point out another thing. We assumed that the electric field did not extend beyond the plates, and deflection starts at 2 centimeters. Okay. If we look at V0y, we can see that there is a deflection. It already has some upward velocity. Not a lot, but some. Okay. And we can see that the intercept is not 0 until you look at your uncertainty. Okay. The uncertainty in that intercept is larger than the coefficient. So my actual intercept goes somewhere from negative 0.10 to positive 0.58. So that 0 is quite possible. So what we're going to do is I'm actually going to construct another graph. I'm not going to completely clean this one up and put axis titles on it. I just want to show you what you can do. Select your X series. Select your Y series. Now I'm going to add my trend line again, but this time when I add it, because I know 0 is in range and it should theoretically be 0, I'm going to set my intercept to 0. You can only do this if you know that your intercept should be 0. And in fact, after you do your regression, it is 0. So now I'm going to do another regression. I'm actually going to do the exact same thing, but check down here. See where it says constant is 0? I can set that. I'm going to change where it displays. I don't want to override. I want both of them there for you. I'm going to say OK. Look what happened here. It tells you that the intercept is 0. It forced it to 0. Again, I'm going to fix my sig figs. You'll note that on A over 2, I have picked up an extra sig fig. What I'm doing is I'm going to copy the formula so I don't have to manually do it. And now I have this. Okay. That's the basics of the analysis. If, when you go to do your regression, you do not have this data analysis tab, what you're going to do is go to File, go to Options at the very bottom, click on the add-ins. It should say Manage Excel Add-ins, say Go. Check the Analysis Toolpack in the Analysis Toolpack VBA and say OK. Sometimes when you don't have it there, you're going to go in and it's actually going to be checked already. For some reason, it forgets it's there. Uncheck it, say OK, go back in, recheck it, say OK, and it should be there. The other thing is make sure you're in a blank cell when you go to regression. Those are the common problems. Okay? So at this point, you should be able to do your analysis. I'm going to stop screen sharing and I'm going to stop recording. You guys have a good day.